Section 2.2, the slope of a non-vertical line. Mathematicians use the term slope to represent the measure of the steepness of a line. We will explore the topic of slope in this section because it has many real-life applications. Aside from steepness, a lot of us know slope is also referred to as the rate of change. So we want to be able to use both of those as working definitions for slope: steepness and the rate of change of a line or linear situation. Let's talk about a formula that will help us find the slope of a non-vertical line passing through 2 points, point x1, y1 and point x2, y2. The symbol we use for slope is little m, and that's pretty standard throughout all of mathematics. Little m stands for the change in y divided by the change in x, or the second y value minus the first y value divided by the second x value minus the first x value of your two-ordered pairs. Notice right here in parentheses that it says x2 cannot equal x1. If x2 and x1 were equal, it would produce a 0 in the denominator, thereby making the slope undefined. We'll talk a little about that later. Our first example, we just want to find the slope passing through the point -1, -2, and the point +7, +8. So first, let's write down our formula. M equals y2 minus y1 divided by x2 minus x1, which in this case is 8 minus -2 over 7 minus -1. 8 minus -2 really becomes 8 plus 2, which is 10, and 7 minus -1 is actually 7 plus 1, which is 8, and that will simplify down to 5 over 4. So the slope between those 2 points is positive 5/4. We always represent slope as a fraction in lowest form unless you're specified to do otherwise. Notice the comment down here at the bottom. When you calculate slope, always subtract the y values and the x values in the same order. Most of us use second y minus first y over second x minus first x, but it will also compute the same thing if you put the first y first and say y1 minus y2 over x1 minus x2. If you mix them up and put one of the y1s first and the x2 first, you would get an incorrect result. So be very, very careful that you're subtracting in the same order on top as you are on bottom. Now we want to talk about how to find the slope from an equation. Let's look at the equation 5x plus 2y equals 10. Most of you probably have learned that if you isolate the y, that will put the equation in slope-intercept form, and then you can easily see what the slope is. So for example, we can subtract 5x from both sides, and that gives us 2y equals -5x plus 10. Finally, we divide both sides by 2, and we simplify the result. Y equals -5/2 x plus 5. This is called slope-intercept form. We'll talk a little more about it later in the chapter. For now, you just need to understand that the coefficient of the x, the -5/2 here, that is the slope when y is by itself. So in this case, the slope is -5/2, which answers the question that was asked. This number over here, the +5, is the y value of the y-intercept. That's one way we can find the slope from an equation. Another way, and it is a shortcut, so be very careful about using it because it only works when the x and y are on the same side. When x and y are on the same side as they are in the original problem, that is called ax plus by equals c form. So in this case, the 5 is the a, +2 is the b, and 10 is the c. If an equation is in that format, you can always find the slope by taking the opposite of the a value and dividing by the b value, which in this case is -5 over +2. And you can see that's exactly the same result we obtained when we put it into slope-intercept form. Just be very careful because a lot of people make more mistakes when using the shortcut. So if you're in a situation where you're not pressed for time, it is recommended that you work it all the way out and convert all the way to slope-intercept form and then identify the slope. If you are pressed for time, go ahead and try the shortcut, like on the ACT or something. Example 3. Example 3 says if carpet costs $25 per square yard plus a delivery charge of $30, then the total cost, C, of N square yards is given by the formula C equals 25 times N plus 30. We would like to graph the equation and interpret the slope of the line. So we are talking about C equals 25N plus 30. Now, N is acting as our independent variable. So he's going to go along the x-axis. So down here, these are going to be my N's. Then the cost is acting as my dependent variable. So I'm going to let the cost be over here on the y-axis. Before we start graphing, it isn't technically in slope-intercept form, but before we start graphing, we need to talk about setting the scale. We don't have a very big graphing area here, so we need to determine a scale that's going to work for us with this problem. These numbers are pretty big, so we know that we're probably not going to want to count by ones. And the best way to determine scale is to just make a table of values and see what you need. See what kinds of numbers you need for your x's and what kinds of numbers you need for your y's, and then you can establish a scale that will work for you. So let's do that. Let's make an XY table or an independent-dependent table. In this case, N is acting as the X and the cost C is acting as the Y. So if I don't buy any carpet at all, if the truck just makes an empty run out to my house, that's 25 times 0 plus 30 is 30. So I would still have to pay the delivery charge of $30. Then if I buy 1 square yard of carpet, that's 25 times 1 plus 30 is $55. So it would cost me $55 to buy 1 square yard of carpet and have it delivered to my house. 2 square yards of carpet would be 25 times 2, which is 50, plus 30, which is 80. And let's do 1 or 2 more. 3 square yards. 3 square yards is 25 times 3, plus 30, which is 105. And 4, if I substitute 4 in, 25 times 4 square yards is 100, plus 30 is $130. Notice that I didn't use any negative values for N because in this situation I can't purchase negative square yards of carpet. That's also why we have limited this graph to quadrant 1 only, where everything is positive. So if I look at the N values in my table, it looks like I really just need to get from 0 to 4. And the best way to do that is probably just to count by ones along the independent axis. So we have 1, 2, 3, 4, 5, 6, 7. Now we need to decide a scale for the y's, and you don't have to have the same scale on the x and the y axis, independent versus dependent. So the cost here is ranging from 30 to 130. So we just need to decide what we want to count by. How about we just count by 30 and start from there? If we do, this is 30, 60, 90, 120, 150, 180, and $210. Once we have our scale established, it'll be pretty easy to put the points on. 0, 30, 1, 55, which is maybe about right here, and it is just kind of an estimation process. 2, 80, 3, 105, about right there, and 4, 130, so somewhere just above 120, maybe about right there. And you can see that that makes a pretty decent line, and that's what we were expecting our trend to be because it was modeled by a linear equation. So here's a line with a positive slope. Now notice, I don't extend beyond this point right here because that would take me into the negative numbers of square yards. So we want to stay with strictly positive over here. Finally, it asks us to interpret the slope of the line. Well, the slope is positive, indicating that as n increases, so does the cost. And certainly that makes sense. As you buy more and more carpet, your cost is going to increase. The actual slope in this case is positive 25, which means that for every yard of carpet I buy, my cost increases by $25 more. Look over here. You can see that every time I increase 1 on the ends, 0 to 1, I increase 25 on the C's. 30 plus 25 is 55. And then it happens again. As I go from 1 to 2, 55 to 80 is also 25. So the slope just tells me the cost of 1 square yard. For example 4, we know that it takes a skier 25 minutes to complete the course shown in figure 2-22. This came out of your book, but I've copied it onto here for you. Find his average rate of descent in feet per minute. So those are going to be the units when I'm finally finished. And we would like to find the average rate of descent. Now, average rate of change is just another algebraic phrase for slope. If you're talking about a linear situation and you're asked to find the average rate of change, well, actually it'll work even if it's not a linear situation. The average rate of change is always found by taking the starting point and the stopping point, or the initial and final point, and finding the slope between them. And in this case, they actually gave us those 2 points. They said at a time of 0 minutes, this skier was 12,000 feet in the air. So he was up 12,000 feet high on the mountain. Then he started skiing down, and 25 minutes later, he was at 8,500 feet altitude. So those are going to be our 2 ordered pairs. 0, 12,000, and 25, 8,500. If I just find slope between those 2 ordered pairs, that's m equals 8,500 minus 12,000 divided by 25 minus 0. And on top here, those are my y values. Those units are the feet. You can see right here, y in feet. So that's feet per, and on bottom, those are my x values. And those are in minutes. Feet per minute. If I simplify that, we have negative 3,500 divided by 25, which I believe is negative 140. And we put our units on, feet per minute. So this skier, his average rate of descent, it's descent because he's coming down the mountain. His altitude is getting less as he goes on. And that's also why it's negative, because if we model this way, it would have a negative slope. He's going down the mountain. So his average rate of descent is 140 feet per minute, and the negative sign is used to indicate that he is descending.